Hello, so welcome to the second portion of our lectures on memory management and virtual memory. So we will talk about page replacement. What do we mean? Now in virtual memory system, we remember that it's we had a physical memory, okay, which is split into pages of the same size, and then we talked about how we bring in the pages from disk, or how we can create pages, and this was called, if you remember, demand paging. Okay, meaning that depending on the access pattern, we would bring in pages into the physical memory. Okay, and we said that we do this based on the demand. It means that a page on a disk, or like another basic page, is never moved into the physical memory unless it is accessed. Okay, so we had discussed how this demand paging worked basically in the previous lecture. Now in this lecture we will talk about what we call paging out. Okay, when the physical memory becomes full because we were always paging in new pages, then it will become full. Then we need to kick out some of these pages. So we call this page out. Okay, and this is also called evicting a page, and we call this page replacement. Okay, so the question is, which if all the page frames of the physical memory are full, then which pages should be kicked out? Okay, and what do we do when we kick out a page? Or the question of, how do we decide how much memory, how many pages should we allocate to a certain process? What is the criteria? So this is the main topic of today's lecture. So let's work out on an example. So at this time, let's assume that we have a process, and this is the corresponding page table for that. Okay, and when we look at this page table, remember that the page table is indexed by the VPN, and the page table, so this is the page table, reflects the virtual memory layout of the process. And let's assume that, like initially, as we have learned, that none of the pages are moved into the physical memory. Okay, so let's assume that the first two pages here corresponds to the code section of our executable. The second one corresponds to the initialized variables, and then we have a page for uninitialized variables, then we have heap, and then stack. Okay, now initially all the pages of in the page table are invalid, meaning that none of them are brought into the physical memory. So I mark this valid bit as 0 for all of them. Now in the page table entry of the corresponding virtual page, if it was 1, we would put in the physical page number. If it's 0, then we put in some information that tells us how to create that particular page. For example, let's talk about this the code portion and the initialized variable. So note that these two portions, they are basically, we can map them onto our executable. Okay, so in this particular case, we say that when the page 0 is here, we say that we also in this page table entry, there the executable, in our case the code portion, is that the C1 and C2. Let's assume that they reside in disk blocks 10 and 11. Okay, so what we say here, we say like it's on disk. Okay, and the block number is 10. Okay, and for the second part, it's C2, that's disk block number 11. Okay, and for the initialized variables, let's say that that's the third block on the disk, again part of the executable. Let's say that it's in disk block 42. Okay. Now for all the other ones here, including stack and uninitialized variables, so first these ones are, we don't have anything because they're not used, okay, and maybe this is also not used at the beginning. With the uninitialized variables, we allocate space, but this space is not, we cannot map this onto a disk block because in this particular page should be created its base effectively all zero. So we mark this with a zero page, okay. And initially, of course, like the stack is not being used, so it's also basically like in this case, like when we are starting with stack, we also mark this with a zero page, meaning that we have to create a zero page, which can then, like you can imagine that I have my disk, right? And instead of basically mapping them onto these actual disk blocks, what I can assume is as part of this disk, I can assume that there is this zero page, okay, which contains all zeros, and so if I need to get them, then I can be effectively copy this into my physical memory. Now let's look at here's our physical memory, and in this case we have the physical memory contains 4 page frames, and this is the page frame numbers of 0, 1, 2, 3. Now as we start execution, what we do is we access, say, this first page in instruction. It creates a page fault, okay, and when it creates a page fault, then what do? We do demand paging. Demand paging means, well, like it's a page fault, so the whole process stops, and we pick an empty page frame from the physical memory, and then we copy this particular block into our memory. Let's say that we copy this into here, which is just C1. Okay, and once we do this, now we can update this information on the page table. Now it is 1 because we have moved it into physical memory, and now the ppn, so I'll just say ppn is 1, okay, and then now we can use this whenever we access a VPN of 0. We actually we go to ppn of 1 and then access our data as such. Okay, now as we move on, let's say that we get another page fault when we are accessing the second one, and as a result we again look for another physical memory, so it's C2 here, so we bring in and let's put this into here, C2, and then we update the page table. Let's delete this fully, and now it becomes 1, and the ppn is now 3. Okay, and then let's say that we pushed something on our stack. Okay, so when we try to push something on our stack, well, it will create another page fault, and now this is saying that it's a 0 page. What we do is we need to create this page. Now when we see that it's a 0 page, we just allocate a space, and let's say that this is here, and we set it, it's effectively we set this to 0. Okay, or you can also envision this as if there's some kind of a virtual 0 page, okay, which is then copied into this page frame. But of course this is completely visionary. Okay, so when we have a 0 page, we just allocate something here, and then you set the contents to 0, and there you go. So after this, now we update this. We update it. Now we set it to valid bit 1, and now ppn is 0. Okay, and well, let's move on, and we accessed a variable and an initialized variable here, and again another page fault. As a result, we copy this into 2, and we update, okay, these ones. So we said that this is 1, okay, and the ppn is now 2, and by the way, this is now 5. Okay, so far so good, but our physical memory is now full. Now at this time, let's assume that I want to access an uninitialized variable, right? And when I try to access it again, it will create a page fault. Now when I get a page fault, it means, well, it's a 0 page. That's fine. Now what do? Well, since the physical memory is full, I need to kick one of these pages out. Okay, which one? Now that is a matter of policy, and we will talk about some set of different policies and their pros and cons, and that's like we will discuss it later. But now let's focus on the mechanism of basically what needs to be done. Okay, now in this case we need to pick something from the physical memory, and let's say that we pick say which one, let's pick the this one. Okay, so we pick this one to kick out. Okay, and what do? Now this is corresponds to C1, which is the code portion, right? And at this time, once if I when I kick this out, do I have to save the content of the memory to somewhere else? Well, in this case, no, because this is from a code section, okay, meaning that it was never modified. So all I have to do is when I kick this out, I kick this out from my memory, okay, and what I do is I update, since I kicked this from this, I update my page table such that now it's no longer valid, and instead of ppn, what I write is I again write back my executable. I said, disk number 10. Okay, this means that next time I get a page fault for this particular page, then I have to go ahead and fetch it from disk block 10. Okay, now in this case I was basically trying to do like I now kick this page. Now I have an empty slot here. Now since it's an uninitialized variable, all I have to do is I put a 0 in here. Okay, and then I set this, I change this. Okay, now so that now the valid bit is 1 and the ppn is 1. Okay, so this is the main idea that we have here. Now let's assume that as we execute, we had this initialized variable data. Okay, and remember that the initialized variable part is basically in your executable you have code like int x equals 5, right? And what we do is let's update this. Okay, we read when we when we define this as such in our code, it means that in the executable, which is, if you look at the initialized variable section like block here. In here I have 5 written someplace. Okay. Now as I execute, let's assume that I did x plus plus. Now x becomes 6. So initially it was 5 here, and then I changed it, so it became 6. Let me put this in a different color, so it became 6. Okay, and uh, as a matter of fact, after this, like let's assume that I needed one more page, like because I tried to, like I malloced for the heap. Okay, I malloced some memory from the heap. Now what do I have to do? Now if I want to kick this particular page out, this ppn2, now I cannot do the same trick that I had done for this one. Okay, reason, well, this has changed. The code portion that I had here, I did not save it back to my disk. It's because, well, the code never changes. But this particular page that I'm talking about, now this one is modified, and I have to keep track all this. And as a matter of fact, like in this page table entry, you have this modified bit, okay, which marks that it's modified. Now when it's modified, what I have to save this when I'm paging this out. Where do I save it? Can I save this particular page when I page it out onto the executable here? Well, no, it's not possible because it will change the initial value of x. So, but I still have to save this. Where do I do that? So for this purpose, we have allocated some portion of the disk block, which we call swap. Okay, so when I page out this one, I page this out back onto some location. Okay, so we have this in I and 6. Okay, and after I save this, okay, now I can, for this power, for this skin, I can remove it. Okay, and then now I can clean this out. Okay, and I set this to 0 because it's no longer in the physical memory. Now I have to tell where to fetch it next time I have a page fault on this. Now in this case I said disk block number 15. Okay, you got it? Okay. And in the meantime, like since for the heap, then I allocate that particular page to my heap, and I set this to 1, and then I set that ppn is 2. Okay, and I set this again to 0. Okay. Okay. Now, what would happen after doing this if I access, if I access, let's delete this again. Okay. Now, if I access this page again, meaning that I wanted to execute, say x minus this time, what do? Now it creates a page fault, so I have to again kick some page out. But where do I read? Now in this case, when I try to page in this particular page, now let's assume that we kick another page. I'm not going to do this, but this time I will be basically using this swap page to put into the physical memory. Okay, so this gives you a crude feeling about the mechanism of why we need paging in and paging out. And what we call as page replacement is when the memory is full, just like in this case. Now, how do we pick which page to kick out? That is a matter of policy. So let's go over the slides after this example. So how does it work? How does this page replacement works? So the first idea is we want to find the location of the desired page on the disk. So when I went to replace means, you have to replace a page from the physical memory on so let's say that I have, so this is my disk here, okay, and this is my physical memory. So the first thing is you find where the page that you want to page in. Okay, you find this. And then in here, then you need to find a free page frame. Okay, if there's a page frame, you just write it, you opt and use it. Okay, if there's no page in here, no free page in here, then what you have to do is, well, it's because you have this one full with something else. Then you pick a page, like there are a lot of pages here, and we call the page that we picked as the victim, okay, because we are going to kick this out, okay. And after this, well, you have to kick this out, okay. There are different ways. One way is you can just discard it. The other way is you can write it onto the swap. It's all possible. And once you kick this out, then you can now move this one in here, and then after that you restart the process. Okay, so the goal of the page replacement algorithm is basically to evict the best page. Okay, and in doing so, what is our goal? Our goal is to reduce the page fault rate, because each time you have a page fault, you need to access disk, and that will slow down the whole system and it will cost you millions of cycles. Now, when you think about what are the pages that's to be kicked out, well, the best pages that will be kicked out are those that will never be used again. Okay. Now, this looks like, well, I mean, like it is possible, but if I cannot foresee the future, and if you're not on Oracle, you cannot do that. It is impossible to know, okay, when a page will be accessed. Okay. Now, if you have information about future access patterns, then you can basically find it is possible to prove that by evicting those pages that will be used furthest in the future will minimize the page fault rate. Right. Okay. And we will see that but the reality is we do not have these future access patterns. So how can we make this work? Now, the best algorithm for this, again, there are a set of policies for this, will be a matter of policy, and we will discuss them as in the upcoming slides. It used to be a very hot research topic, but nowadays it's widely considered solved. Now, the way we do this is again the same thing as we did with cache. If you remember, in the cache memories, we had a cache memory here, and below we had a larger memory. And the question was, so this was my cache, and this was my, say, memory, and which pages, which blocks or data or whatever you wish to it, which one should be moved onto the cache, because accessing cache was faster. And in doing so, we exploited locality in our programs. The first one was temporal locality. This is locality in time, meaning that memory accessed recently tends to be accessed again soon. Okay, so let's say that this is your time access. Okay, and if I am at this point in here, it means that like the likelihood of pages that were accessed in the near future, like these pages that were accessed here, they are more likely to be accessed. But a page that was accessed really in the past, like this one, is likely not to be accessed soon. Okay, so this is what we call a temporal locality. And then we have spatial locality, meaning that memory locations near recently accessed memory is likely to be referenced soon. So this is, this was in this case it was T, and in this case let's look at say that this is the memory address. Okay, and let's say if I'm here at this time, I would claim that the memory locations that are near me are likely to be accessed soon. Okay, whereas if I have a memory location that's far from my current memory, then it will not be as such. Okay, now let me just do for completeness, let's do the same trick in here. So let's say that this is my time, this is where I'm in my time, and these are the this is the recent past and this is the further past. Okay, so as we will see, locality helps to reduce the frequency of paging. Okay, and it means that if you want to keep something in the memory, then it should be used many times. Now this depends on many things. Like we have to look at the amount of locality and reference patterns in a program, and as a matter of fact, once you know this, then as you code, you want to maximize temporal and spatial locality in your programs. And of course, it depends on the page replacement policy and also the amount of physical memory and what we call the application footprint, the minimum amount of memory that a program needs to run without creating a page fault. So let's look at them. So before we move on, we have to find out basically how these page replacement algorithms can work. Well, they will be operating on some data structures that represents the physical memory. So here is what we call an inverted page table. So imagine like an array which is indexed by ppn, and in this case what we can do is for each ppn, so this corresponds to the zeroth block, zeroth page frame. This is the first page frame, second page frame, and etc. So this data structure is the size of it is determined by the size of the physical memory. And on this, then we can mark the pages that are allocated to some process as like in blue, and the ones in white here, they are free. Okay, now how can we get this? Well, such a data structure you can create by going over all the page tables of different processes. So here we have our page table. See, for process A, here's my page table for process B, and if you remember in these page tables, we had these page table entries, okay, and here's our valid bits here. Now all I have to do is I have to go over these page tables, and I can look at the pages with 1, the valid pages here, okay, and let's say that I have 2 in here. And then look at the ppn values, because when this is 1, then I have a ppn value, say that this ppn value is 0, and this one has a ppn value of say 7, and this one has a ppn value of say 4, and this one has a ppn value of say 5. Okay, and now as a result, once you go over all of them, then in this basic list you can say that, so this is my ppn, this is indexed by ppn, this is 0, 1, 2, 3, 4, 5, 6, 7, 4, 5, 6, 7, and etc. And once I read them, then I can put these values. So this one's I believe that this is full. Okay, 7, that's also full, and 4 is full. Okay, and 5 is full. Okay, so the remaining are empty. Okay, so we need to get this structure. We can obtain this structure by going over all the page tables of all processes. Okay, now this one can be a bitmap, meaning that you can have a 1 or 0 for each physical page frame. Okay, it will require 1 bit per physical frame, or it can be more involved. For example, it can include a reference count for each page frame. And if you remember our shared memory or call, you may imagine that, and let's again draw this in here. So I have these two page tables, page table A, and here's my page table B. And if you remember, after fork, or like whenever you have some shared memory, then you have this valid bit is 1, and you may have the very same, so I'm saying that like this, I say 7, and you can have the same 7 here. Okay, so in this case you may wish to keep track of in this case that page 7. Okay, so here's our structure that you can in here. So this is my 7. So this is, I mark this as being used. Now once this process is gone, now this page frame should not be unallocated because it's still being used. As a result, that's why we need to keep track of, along with this one, you also need to keep track of the number of reference, in this case 2. Okay, and this is essential for if you have shared memory or copy on write. Okay, or so we can implement this using basically pages as a free list that I will show in the next slide. So as I said, this whole structure is also called as an inverted page table. Okay, that means that I have 1 entry per physical page. Now there are a number of representations, and we will focus on basically 2 representations. One is bitmap representation, or for the free physical page frames. Okay, and in the case of bitmap representation, let's talk about an example where we have a physical memory of 4 GB, that is 2 to the power 32. And let's assume that the page size, it's not given here, but it's the page, like the page size is given as 1 kilobyte, which is 2 to the power 10. Now, how many pages do we have in the physical memory? Well, the number of pages is basically 2 to the power 32 divided by 2 to the power 10, which is 2 to the power 22. So that is roughly 4 mega pages we'll have for basically this many pages. Now, if I use a bitmap representation, it means that I will be using 1 bit per page, or I'll be using 1 byte per 8 pages. So by dividing this with 8, or to the power 3, it means that my bitmap representation will consume 2 to the power 19 bytes, and that's the bitmap size for me, which is half which is half a megabyte. Okay. Now the other way to represent this is to have a linked list of page structures. In this case, we have a free list, and these are pages. Okay, and what we do is, in this case, in each page you can store the numbers and other information about empty pages. Okay, so for example, in this particular page I can see that my page, say page 7 is empty. Okay, and maybe like page 8 is empty, page 10 is empty, page 12 is empty. Once this is full, then you can point, like it's a linked list, so you point to the next one, and then you can follow this up to 9 and 11 and etc. until here. Okay, now we can store this information. This is stored using the empty page frame, so it doesn't actually consume like memory. As your memory gets full, this free list, linked list becomes shorter and shorter. Okay, and the nice thing about these structures, as opposed to the bitmap representation, is you can keep the reference count, reference to task memory points, and etc. Okay, now let's talk about some page replacement algorithms. And as we said, there's no one good algorithm, but we will be discussing a set of them. And we will start with the random algorithm. The random algorithm is when the memory is full, you kick out a random page. You page out a random page frame from the physical memory. Obviously, it's not the best one, but it's obviously very easy to implement. Now, why do we bother to talk about this algorithm at all, you may think? Now, the reason behind this is that this creates us a baseline to compare other algorithms that we will be devising. Now you can imagine that in in this page replacement algorithm, we want to minimize the page fault rate, right? And let's say that somebody comes up to you and says that, well, I have devised a really good page replacement algorithm, and if you run your program in it, then you will get, say, 32 page faults. Okay. Now, is this a good value or not? Well, by looking at this number, you have no idea. Is it a good rate? Is it a bad rate? Now, that's where setting a baseline is really helpful. Now, in this case, we have this random algorithm, which should be like when we have the same when we use this random page replacement algorithm, and then check how many page faults do we have. So if you look at our performance rate, so this is our performance, okay, and in this case, the random algorithm, when we run it, whatever number it gives, okay, let's say it gives a number of, say, 30. Okay, now this gives you a baseline, meaning that you should do better than this, and in the case of page fault, then we should do less than this. So if your friend who claims that he has done a really excellent job by creating 32, now you know that 32 is actually not a good value, but it's because here we have this 32 is basically bad. Okay, this is bad. Okay, and there's this one, it's good. Okay, now the first algorithm that we'll be talking about is first in, first out. It means that we keep track of the order of page ins and then throw them out in the order that they were paged in or they were allocated. So we maintain a list of allocated pages, and when the length of the list grows to cover all the physical memory, then we pop the very first page off and allocate it. Now, why can this be a good idea, or why might this FIFO be not good? Well, you can imagine that we should do this discussion based on our idea of spatial and temporal locality. So in terms of temporal locality, it's good because we know that something that was paged in a long time ago is actually that does not is very far away in time, and as a result, when we use this first in first out, then we'll be kicking pages that were allocated at the beginning of like a long time ago. But there are also cases that you can see that in the first in first out you really don't care about spatial locality. Okay, and as a result of this, you may end up performing badly in this one. Now let's move on. Okay, so in particular with the FIFO, one problem that we will have is that it suffers from something that's called Baladi's anomaly. And this is an interesting anomaly, meaning that the performance of an application might get worse as the size of the physical memory increases. Now, this is completely counterintuitive. If you put more memory into your computer, you expect the number of page faults that you get be less, correct? Now, Baladi's anomaly is saying that if you are using first in first out, this may not happen, and that the performance may actually get worse. Now, I'm saying that it may get worse. It will not always get worse, but there is a possibility that it may get worse. Now, let's look at how this occurs in a simple example. So here we have an access pattern, and by access pattern, these are the PPNs that we are accessing. Okay, so we are accessing page 0 at this time, and here we have the physical memory. In this case, this is our physical memory. It has 3 page frames, and when we access 0 pages, there's nothing here, so it creates a page fault, which is shown in blue. Okay, here we have a page fault. Now page, in this case, it's brought in. Now we are fine. At time 1, then we access. Sorry, like at time like this is. Let me just mark this is time 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and 11. Okay, so this is the time axis, and these are the access, these are the PPNs that I'm accessing. So at time 1, I accessed frame 1, and it will create a page fault, and it's brought in, and I put it in here. And then at time 2, again 2, it creates another page fault here, and then it's brought in. And at time 3, I accessed 3. Now at this particular time, I have to kick someone out. Which one should I kick out? So we look at here in the order of the access time when I access this. Now the one that's furthest here is 0, so this 0 is kicked out. So in this case 0 goes out, it's paged out, and as a result 3 gets in. Okay, and now if I access 0 again, now at this time, like among 1, 2, 3, which one is the which one was is at the top of that? Now 1, so it goes out, and instead of this I put 0 in. Okay, and you can see that these are all page faults that I'm having in here, and then 4, and then 0, and so on. So this is the pattern of PPNs. This is the pattern of PPNs in time. Now let's say that I run the same process on a machine, but this time I have 4 page frames. Okay, and when I do the same first in first out that's being applied, so this is here we're using first in first out in this case as a page replacement algorithm. In the first case, when I had 3 page frames, I had generated 9 page faults. In the case of 4, I generated 10 page faults. Okay, so this is basically what we call Baladi's anomaly. Okay, and that's why first in first out is not a good algorithm for page replacement. Now, we said that the random algorithm created a baseline for us, meaning that if this is my performance system, so this is my performance, okay, and you can say that this is the number of page faults, okay. Now we said that if I run my random algorithm and it creates whatever number, like a number of page faults, so if it's here, then this is my baseline, okay, okay, and anything that does worse than this, okay, this is like, any algorithm that creates more page faults than a random page replacement algorithm, this is actually really idiot. This is dumb. Okay, let's call this. Okay, but you may wish that, well, okay, my performance is as such. Of course, ideally I want to have 0, but I know that this is not possible. So what is the best that I can do? So in order to find this value out, we have this algorithm that's called optimum or minimum. Okay, in this case we assume that the algorithm can foresee the future. So if this is the time access pattern, okay, and if this is time, okay, then the algorithm at this time, if it's here, so we access say 0, 1, 3, 4, 0, and etc., and 5. And at this time, the algorithm also knows what will be accessed. So this is our current time. Let's call this T0. And it can foresee the future and the pattern that I will have here. Okay. Now, so, and then makes this decision that it evicts the page that won't be used for the longest time in the future. Okay. So this is really nice. Like if I look at these values, let's say that these are the values, for example, like 1, 2, 3, 0, 0, 5, and then let's say that 2, 1, 5, 4, 0. Okay. Now if I know that this is my future, this is future, and based on this, I can say that, well, given this, I should not kick out 5. I should not page out 5 because I will access it very soon. Well, 0, yes, I should kick out, like in this case, like among them in here, 0 will be accessed very far in the future. So I should actually kick 0 out if I need to. Okay. So this algorithm requires that we can foresee the future. So it's an impossible algorithm and it cannot be implemented. But it's nice that it has the provable optimal performance, meaning that if I can foresee the future, okay, then I can find what the minimum number of page faults that I can have. So in this particular case, I will say that if this is the random, this is my baseline, then I will say that I have the optimum algorithm, which is not implementable, okay, and this is the best, okay, but also it's best, but it's also basically unrealistic, because it requires that my algorithm requires access to future, it should be able to predict the future accesses. And as a result, now what I can do is, if somebody gives me an algorithm, then I can match them. So the closer, if my algorithm is here, then I know that it's very close to optimum, and so it's good. Okay, if it's here, I know that there's a long way for improving towards here. Okay, so this is essentially the random algorithm and the optimum algorithm. Random provides me the baseline, and whereas optimum gives me the best, basically the best performance that is but that is unrealistic. So what we can do is we can the first algorithm that we'll discuss is least recently used. Now the idea is, if this is my time axis, okay, and I have a an access pattern, say 1, 2, 4, 0, 3, 5, 0, and then say 1. And if I'm at this point, then I need to kick a page out. Which page should I kick? Now I don't. In this case, this is my future. Okay, and I do not what the access pattern for the future will be. What I can do is I can predict that the future will be a reflection of my past. So let's say that I can say that if I accessed 1 here, then it will be more like 1, or this will be, you just mirror them here, 5, 3, 0, 4, 2, and 1. Okay, so if this is the case, what would the, if this is this is basically what I predicted. Okay, and in this case, how would the optimum algorithm choose? Well, if I'm here and among them, like let's assume that I have all these values in my uh, in my in my main memory, then I can look at here, and among them I would know that, well, if I kick, say, page 2 here, okay, now page 2 will be the first one, like will be, I will need this very long time. This is like the optimum algorithm. I'm implementing the optimum algorithm, but I'm doing this by predicting that the future will be a symmetric of this. Now, this is what we call least recently used, and this applies that, like, if I'm here, if I'm at this point, then it means that I look at all the ones that I'm in my main memory, and I pick the one that was least recently used. And in this case, it's actually 2. It's not 1 because 1 was very recently used, and 0 and so on. Okay, so this is the idea between least recently used algorithm. What we can do is we can keep track of when pages are referenced, okay, and use this behavior to predict future behavior. And this is like the minimum or optimum algorithm used future information, whereas the least recently used past information. This is basically, it's essentially predicting that the future will be a mirror image of that. So we can implement this by recording a timestamp of access every time a physical page is accessed. And when we are choosing the page to evict, then you can scan over all the pages and throw the one with the oldest timestamp. Okay? Now, what is the problem with this algorithm? So we have two problems with this implementation. The first one, this is a problem with space, meaning that if I am storing, say, 32-bit timestamps for each page, then it would create a lot of storage for my page table. Okay, remember that I am storing this. So if this is my page table, okay, and in this case I have the page table entries in here. So here's the valid bit, for example. Here's the valid bit, and then here's the oops, and here's the ppn values. And here I can store the timestamp. Okay, so each time I'm accessing this page table, this is 1, I have some value here, and you update this page stamp. Okay, now this would make my page table quite a lot, because if you do the computation, uh, your page table may double in size. It depends on basically the how many bits you are using for ppn and other things, but it may actually double the size of every pt. Okay, so that's the space constraint it will take, and as a result, since we want to keep these page tables in the main memory, then it means that I will be using most of my memory to store this particular the page tables. And the second problem that I have is related with time, meaning that once I have this, then how do I find the page table entry with the lowest timestamp? Now this will be again huge, right? We can do the computation. If I have, for example, imagine that for each process, if I have 2 to the power 10 entries, and if I have, say, say 100 processes, then this would be the number of items that I need to do some sort of a sorting, and this can be okay for something else, but you can imagine that this is a time that I want to page in a new page for a process who's demanding it, and I'm looking for how I can kick out, which page should I be kicking out. So this will take a long time. So the space and time complexity of this implementation is actually a major limitation. How can I approximate the least recently used algorithm? We can, as I said, it had two problems in terms of the space complexity and the time complexity. To address the space complexity, I can use the page table entry reference bits and a small counter per page. So when we have this page table entry here, which had this valid bit and other bits here, and here I have my ppn, then I can use my reference bit, okay, and maybe like it can be a couple of bits size, like 2 or 3 bits in size, and I can store this in my page table entry. Okay, and what I can do is I can periodically, say every 100 milliseconds, then scan all the physical pages in the system. If the page has not been accessed, which I can find out by checking out the reference bit, okay, with 0, then I increment the counter. Okay, so here we have the reference bit here. Okay, here's the reference bit, and here's the counter. Okay, and whenever an access, like initially it's 0, whenever it's accessed, then you set it to 1. Okay, and every 100 milliseconds, then you uh, increment or shift right the counter by here. So I can have a counter of like 0 0, and whenever it's if it's not accessed, well, let me just do this in here. So if the page is accessed with reference bit 1, then you set the counter to 0. Okay, if it's not accessed, then you increment the counter. So and in each case we clear the PT reference bit every time, once we do this check. Okay, and at the end of this, then the counter will contain the number of scans since the last reference to this page, and the PT that contains the highest counter value is the least recently used, so we check the one with the highest counter. Okay, so here's an example of this. So this is the time axis, time is going here, and these are the page frames. So this is, for example, so this is the ppn 0, 1, 2, 3, 4, 5, and so on. Okay, so during the first, say, 100 milliseconds, the ones like 0 is accessed, the ones in blue marked in here, they are accessed. Okay, so these are accessed, and as a result, during the scanning process, if something is accessed, its counter remains at 0. If it's not accessed, then it is incremented by a 1. So these ones, it's not accessed, it's incremented to 1 and so on. Okay, so this is done, say, every 100 milliseconds. And after that, we again do our access, and during the second 100 milliseconds, then now at this time, this one is accessed. Okay, the ones in blue are accessed. Okay, the ones in white are not accessed. So since this is accessed, like we reset it to 0. Now in this case, this particular one, it was not accessed, so you increment it to 2. This one, it was 1 because it was not accessed before, but now during this cycle it is accessed, so you reset it to 0. Okay, now this was not accessed, like this. This was accessed in the previous one, and also it goes on. So not accessed, incremented to 1, not accessed to 2, and so on. Okay, so based on these ones, then I can find the highest counter value, and then I can evict these pages. So in this case, I can evict any one of these 4 pages. Okay, so this is not it's not vast implementation, but it is something that that solves the space problem basically. In this case, let's see. So this is basically solves the space problem, or space complexity. Okay, because it uses very few bits. Now, it uses space complexity, but nevertheless, it doesn't solve the time complexity, meaning that when I have this, I still have to do a sorting over basically over all this array, which may require quite a lot of time. Now, that brings us to our second algorithm, which is called the least recently second chance algorithm, or it's also known as the clock algorithm. Okay, now the way it works is it keeps basically the least recently used, it keeps what we call a clock hand. Okay, and the idea is the clock hand scans over all the physical pages in the system. Okay, and so it goes in here, the clock hand, it moves from one end to the other one, and the way it goes is it executes this algorithm. If the reference bit is 1, okay, meaning that that particular page was referenced. So in this case, the reference bit, in this case, let me do this. The reference bit was 1. Okay, so it says, okay, you were referenced during the last period, so I'll reset it to 0, and then I'll give you a second choice, and then it moves on to the next one. And this one, it's also, so you set it to 0, and then moves on to the second one. Okay, so and it moves on by resetting their clear bits. Okay, and when it comes to this one, now this one is not let's say that its reference bit is 0. Okay, now at this time you evict this page. Okay, meaning that you kick this guy out. Okay, and then you move on. Okay, now when you do this, remember that in this case I was at here, so my clock hand now remained in here. Now after a certain time I need to evict another page. Now the way I go on is I start from my current state. Okay, and then I do the same thing again. Look at the reference pad, the reference bits. It's 1, so I clear and set it and say that, okay, I move on to this one. Clear, move on to the next one. Clear. Now this reference bit 1 was this, so you kick this guy out. Okay, so this is nice because we don't need any counter in the page table entry, and that's nice. The second thing is in order to kick out a page, I do not have to go all over of all the pages in here. Okay. Now, obviously, this is not um, perfect, but it is fine. It's also called the second chance algorithm, meaning that it has this clock hand which scans, and each time it encounters a page that was accessed within the previous time, it resets it to 0 and says that okay, I'll give you a second chance, and then until it finds a page that is not that was not accessed, and then kicks this guy out. Okay. Now you can see that this is a lot like the least recently used, but it operates in an iterative fashion, meaning that it just in order finds a page to evict, it starts scanning from the current clock end. This is important. It's the current clock end. This is what we do. Okay. Now what happens if all the pages have their reference bits set to 1, meaning that they were all accessed? Well, what will happen is, if this is my read pattern, okay, you go here, you go all the way, you reset it, and then when you come back, now you'll find that the reference bit is 0, so you kick this guy out, okay? And it's so there's a slight variant of this one, which is the nth chance clock, meaning that we only evict the page if the hand has swept by n times. So you keep a counter again. You increment the per page counter each time a hand passes, and the reference bit is 0, and evict the page if that counter is greater or equal to n, and the counter is cleared to 0 each time a page is used. Okay, so what this does is this one basically addresses the time complexity because it doesn't go over all of them. This algorithm can even act even smarter, okay? And what it can do is we can look at the reference bit. Remember, the reference bit is set whenever that page is accessed, okay? So it can be read. So reference means, let's do this. It's basically if a page is read or written, okay? All right. So it will be set, okay? But then there we have another bit called modified bit. So this is set only when that particular page is modified, okay? And we can use these both of them as an ordered pair to classify pages into 4 classes. So the first class is 00, meaning that it's not recently used. So this is the reference bit. So this is the reference bit, and this is the modified bit. Okay. So 00 means it's not recently used and it's not modified. So this is the best page to replace. Okay. And 01 means it's not recently used, okay, but it's modified. Now, when a page is modified, it's not quite good because if I want to kick this page out, then I have to write this page onto disk before replacing it, okay? Because otherwise that whole page will be lost. And now the other option is I have a page that is accessed recently, but it's not modified. Now, so this is, we call this a clean. It will probably be used again, but kicking this out does not require writing back onto the disk, okay? And the worst thing is 11, meaning that this is recently used and also modified. So this is worse because in the near future it will be probably used again, but also the page has to be written out before it can be replaced. Okay, so this is basically, these are the things that we have to think about, and we may need to scan the circular to queue several times and to minimize the number of required input outputs. Now, what happens to a page when we choose the one that we choose to evict, to page out? Well, it depends on what kind of page it is and what state it is in. Now remember that this is our virtual address space. And in this virtual address space, for the pages in color here, okay, they are mapped onto our physical memory. So each of them corresponds to one or more pages, okay. So the ones in color, they are mapped onto the physical page, and the ones in color, you can imagine that for the ones here, it's basically the ones in color. Let's say the valid bit is 1, and we have this ppn value that is basically set. Now the one that's in here, this black ones, the black ones are what we call holes, okay. And for these ones, we have the valid bit set to 0, meaning that they are not brought into the physical memory yet. So as a result, they point in when the valid bit is 0, they either map to basically disk or they map to what we call a 0 page. Okay, meaning that in this part, if the valid bit is 0, and then if I have a page fault because of this, then what it means is I need to generate how I can handle that from disk or by creating it from 0. Now this portion of like the code and the initialized variables, we probably will map them onto our program executable. Okay, these are blocks that correspond to our executables. Other portions, like these, let's see this. This is the code section, and this is the initialized variable section. We may be mapping them in here. Now, then there are other sections, the holes here, which I map them to 0 page. 0 page means if I get a page fault in this region, all I have to do is I allocate a space in my physical memory, and then you clear the contents to 0, and then set it as such. So this is like, on my disk, I have a page that is filled with zeros, and you effectively copy that 0 page onto the physical memory. Okay, and then there are other parts, things like, for example, look at the stack. Okay, now in the stack, these portions are mapped onto physical memory, no problem. But then, like the holes in the stack are effectively swap files. What do we mean by this is, when I page out a stack page, then I have to write this to the disk. Where do I write it? Can I write it on the executable? No. Well, but I have to write it because eventually in my stack, when I page them, when I have to page them in, I need to read it. So I cannot lose the information in this region. So what I do is, if I pick this page to page out, I write this onto a special place called like swap, and this is effectively another block on the disk, and so you keep track of these pages such that it executes, it can be brought in from here. So what we do is, here we have our swap files, and the way we do that is in the page table entry format. When the valid bit is 0, okay, now we can use this information. So here we have the valid bit is 0, and in this portion of this, then I can use this to mark them, to point it out where the corresponding data is on the disk. Okay, so this is one representation, that we have a 5-bit swap file index, and here's an offset. So this effectively says that, like tells you on the disk where is it, okay, if I want to bring this in. Okay, Note that, for example, when we have executables, like the code part is basically swap is paged in. It never goes into the swap portion because it's never modified. Okay, or is a zero page initially. We don't deal with this, and let's wrap things up. So this is the virtual memory of a single process, and it's consisted of these different segments like the code segment, the initialized variable segment, uninitialized variables, heap, and stack. Now let's see how the page in and page out works for this segment. We have discussed this before, but I want to draw a picture that summarizes all of them. So the first thing is we have the executable. And for the code segment, well, this is where we page in. Okay, this is a sign for paging in. And is there a page out? Well, there's no page out, so I'll draw this as with X because the code segment is never modified. Okay, now with the initialized variables, and this is the part where we have, for example, int I equals 5. Okay, then in this case this 5 value is stored in the executable, so this segment is also paged in from the executable. Okay, and if not modified, and I'll draw this in here, if not modified, then you can discard it as it is. But if modified, then the pages in the segment, and we decide one by one, so let me see it, have to be stored somewhere else when we are paging out. So that place is the swap. Okay, so if modified, then we write them on the swap. So if modified, okay, then we write on the swap, and after that, when it comes to page in, then we page in from the swap. Okay, note that the code segment is never saved to swap because it is never modified. Now, what about the uninitialized variables? Now, uninitialized variables, this is essentially all zeros. It's not part of the executable. Instead, we map them to a zero page. And a zero page is a page filled with zeros, and it's paged in from this zero page. Okay, and if it's when we modify it, if modified, then we again write them into swap. Again, if modified, okay, and then page in from swap. And the same goal is true for the heap. Okay, so I'll just again draw this for the heap, and then again, and also true for stack. Again goes to swap and modified here. Okay. To reiterate what we have done when we are paging out or page eviction, how we evict the page depends on its type. If it's a code page, when we are paging out, we just remove it from memory. That's because we can recover it from the executable file on the disk. Okay, and if we have an unmodified data page, this can be a heap, this can be initialized variable, uninitialized variable, etc. If the page has previously been swapped to disk, then we just remove it from the memory, so we don't do that. And if the page has never been swapped to disk, then we just allocate a new swap space and write the page to it. Now, The exception is when we have an unmodified zero page, and that means that we don't have to write it to swap at all. If we have a modified page, and if the page has been swapped to disk previously, then we write the page out to swap. If the page has never been swapped to disk, then we allocate a new swap space and write the page to it. So this is exactly what we have done in the previous example. Now let's look at the physical frame allocation. When we have multiple processes, then how do we allocate physical memory? And what if a process A needs to evict a page from process B? How do we ensure fairness? And it's important because let's assume that we have multiple users and each of them have their own processes, and you want to be fair to all users. And if a process A is evicting pages because it's creating a lot of page faults from process B, then it will not be good. And so the problem that we have is how do we avoid one process to hog the entire memory of the system. Now, one solution to this is to use local replacement, meaning that we put a per process limit on the physical memory usage of each process. And when that process reaches its limit, then it evicts pages from itself. Okay, this ensures some sort of fairness within that. Or we can have global replacement algorithms, because we can argue that the physical size of processes can grow or shrink over time, and we can allow them to evict pages from other processes. This is fine. But note that one process's paging can impact the performance of the entire system. So when you have one process that's doing a lot of paging, then it will slow down the whole system. So this is not a very clear-cut issue. Now let's define the concept of a working set. Now the working set is for a process is the set of pages that it currently needs. And what we do is we look at the set of pages that the process accesses within a certain time interval, so of size W. So let's say that if this is the time axis, and if I am here, okay, this is my time axis, then what I do is I look at the access pattern, and so this is the time interval that I have here, and you look at the set of pages that are accessed in here. So this is a set of pages that we would need. For example, it can be, say, 5, 7, 8, and 0. Okay, so if it's accessing these set of pages, we call this the working set. Now this set can be changing over the lifetime of a process, and when the process, for example, it's doing some high locality, for example, just looping over the same data and the same loop, then you can imagine there's a smaller working set. But if there are some low locality regions where you're jumping all over the code and the data, then it's a larger working set. Now the basic idea is if we give each process enough memory for its working set, then it will be good for the whole system. And if this working set is larger than the physical memory allocated to the process, then it will swap, meaning it will page out quite a lot. If it's smaller than the memory allocated to the process, then we'll be wasting the memory. And so it will be growing and shrinking over time. Now, how do we determine this working set? Well, one simple approach is to use a modified clock algorithm. So we sweep the clock hand at fixed time intervals and record how many seconds since last page reference. and all pages referenced in the last t seconds, then we define them to be in the working set. Now that we know the working set, now how do we allocate memory? And if working sets for all processes fit in the physical memory, then we are fine. Otherwise, we have to reduce the memory allocation of larger processes. And the main idea is that if you have big processes, they will swap anyway. So we just want to let the small jobs run fast. And this is very similar to the shortest job first scheduling, that we give priority to smaller processes for getting memory pages. And of course, then there's the issue that, how do you set the working time limit t? If it's too large, then you can see that very few processes will fit. If it's too small, then it will spend more time paging out. And which is better? Well, again, this is an issue that that doesn't have any solution. Now, the main idea is we are concerned with the page fault frequency of the whole system. So we want to dynamically tune the memory size of a process based on the number of page faults. And what we can do is we can monitor the page fault rate for each process. And if the page fault rate is above a threshold, then we give that process more memory. So when we give more memory, then it will cause the process to fault less. But note that it may not always work, and like just recall Belladie's anomaly. And if the fault rate is below the threshold, or maybe average, then you can reduce the memory allocation for that particular process. Now we have the way we discussed this. We said that we page out whenever the memory is full, but usually it's too late. And when a free page is required in a loaded system, then you need to, if the system is loaded, then you need to run the replacement algorithm. But then the replacement algorithm then requires I/O, and as a result, the whole thing will be slow. The solution that actual systems have is to have a page daemon or swap daemon that runs in the background, and it watches the system's free memory, and it starts replacing pages, okay, as free memory drops below a threshold. Or when you say replacing, it's basically paging out. So it maintains a pool of free memory at all times, so that tasks requiring a new page can find a new page instantly. And it sleeps when there's plenty of memory, and it wakes up more often and replaces more pages as the system gets low on memory. And in the extreme cases, it may start replacing the whole memory of tasks, which is also known as thrashing. Okay, so the way we do is, when we are paging and swapping, we are effectively moving the inactive pages out to disk, and we have seen how we can do this. And there's this terminology of paging, which is paging in and paging out, and there's the swapping. And usually what we mean by swapping, it refers to moving the memory of an entire process out to the disk, and this effectively puts the process to sleep until the operating systems to swap it back in. And when we talk about paging out and in, it refers to moving individual pages to disk and back, and we use paging, but sometimes we use paging out and swapping interchangeably. So there's no clear agreement on the definition of these things, so we have to be aware of this usage. And of course, like this may have happened to all of us, that when the system becomes more loaded, it spends more of its time paging, and eventually, if you look at the CPU utilization, as the number of processes grow, the CPU utilization grows with it. But after a certain time, you will see the disk light on, okay, and the CPU utilization goes down because it's always paging in and paging out. So the processes are merely using I/O to page in their pages or page out, and this is called thrashing. This means that the system is overcommitted, it has too little memory, and so in this case even the page replacement algorithm doesn't matter. Okay, so what can we discuss? We can change the scheduling priorities to slow down processes that are thrashing, or we can identify processes that are hogging the system and kill them. Okay, and is this a problem on system with only one user? Well, yes, even in that case that happens.